minus 2 x2 is equal to 0 and x2 minus x3 is equal to 0. Here again the first column have leading entry, second column have leading entry, but third column does not have leading entry, so that's why we take x3 is equal to k and put this value in the second equation. We will get x2 is also k and put this value in the first equation. We will get x1 is equal to minus 2k. So thus the eigenvector corresponding to lambda is equal to 1, that is x1, x2, x3, that is equal to minus 2k. In fact this is not minus 2s, either you suppose s or k, right? So minus 2k, k into k, so that is equal to k into minus 2, 1, 1. Okay, so the basically eigenvector is minus 2, 1, 1. Okay, so corresponding to lambda is equal to 1, we will get the eigenvector minus 2, 1, 1. Now we want to find the eigenvector corresponding to lambda is equal to 2. So again we have to do the same process, a minus lambda I. In this matrix you can see, in this matrix minus lambda 0, minus 2, 1, 2 minus lambda 1, 1, 0, 3 minus lambda. In this matrix we have to put lambda is equal to 2. So that's why we will get this matrix minus 2, 0, minus 2, 1, 0, 1 and 1, 0, 1. Okay, minus 2, 0, minus 2, 1, 0, 1, 1, 0, 1, right? So we have to put that lambda, the value of that lambda in the previous matrix, a minus lambda I, in a minus lambda I. So minus 2, 0, minus 2, 1, 0, 1, 1, 0, 1 into x1, x2, x3, that is equal to 0, 0, 0. So again that matrix can be written as minus 2, 0, minus 2, 0, 1, 0, 1, 0 and 1, 0, 1, 0. Now again we convert this matrix into a row echelon form. So we multiply first row with 1 by 2 and add into the second and third row. We multiply first row with 1 by 2 and add into the second and third row. So that's why this matrix become minus 2, 0, minus 2, 0. The first row is as it is. Second and third row become change now, 0, 0, 0, 0. Second and third row, the whole second and third row are 0 now. So in first column we have leading entry, second and third column does not have leading entry. So that's why we suppose x2 is equal to t and x3 is equal to s. And we will get one equation, that is minus 2x1 minus 2x3 is equal to 0. So x is equal to x1, x2, x3, that is equal to minus s t s equal to s will be common out, so s into minus 1, 0, 1 plus t into 0, 1, 0. So now we will get total 3 eigen vectors, right, corresponding to lambda is equal to 1 and 2, 2. Corresponding to lambda is equal to 1 we have one eigenvector, and corresponding to lambda is equal to 2 we have 2 eigenvectors, right? So this question is complete now. That's the question that find the eigenvalue and eigenvectors corresponding to the matrix, and that we already find out. Okay, so this is question number 5 or 5a. Find the matrix that diagonalizes A and determine P inverse AP, where A is equal to 2, 0, minus 2, 0, 3, 0, 0, 0, 3. In fact we have to do with the same process here, but just the eigenvectors we have to convert into the column vector. So that is our matrix P. So the characteristic equation of A is given by determinant of A minus lambda is equal to 0. You can see what is determinant of A minus lambda I, 2 minus lambda, 0, minus 2. Just put it in the main diagonal entries, 2, 3, 3, that are the main diagonal entries, and in that main diagonal entries we have to add just minus lambda, 2 minus lambda, 3 minus lambda and 3 minus lambda. Other entries are same. Okay, so 2 minus lambda, 0, minus 2, 0, 3 minus lambda, 0 and 0, 0, 3 minus lambda. 2 minus lambda, 0, minus 2, 0, 3 minus lambda, 0, 0, 0, 3 minus lambda, that is equal to 0. That is our characteristic equation. Solving this determinant we will get 2 minus lambda into 3 minus lambda square is equal to 0. So we will get 3 eigenvectors, one is 2, second is 3 and third is also 3, right? So now we want to find the eigenvector corresponding to lambda is equal to 2 first. The eigenvector x is equal to x1, x2, x3 corresponding to eigenvalue lambda is given by the matrix A minus lambda I into x is equal to 0. Okay, So 2 minus lambda 0 minus 2 0, 3 minus lambda 0 0 0, 3 minus lambda into x1 x2 x3, that is equal to 0 0 0, and lambda is equal to 2. Put lambda is equal to 2 in this equation. 0 0 minus 2 0 1 0 and 0 0 1 into x1 x2 x3, that is equal to 0 0 0. So we will get x2 is equal to 0, x3 is equal to 0 and x1 is equal to k. Why? Because of solving this matrix into a row echelon form. Okay, convert this matrix into a row echelon form. So you will get easily. This example is actually same as a previous example, right? There is no difference. The method is same. So you can solve easily. x2 is equal to 0, x3 is equal to 0 and x1 is equal to, let x1 is equal to k. So the eigenvector corresponding to lambda is equal to 2 is 1 0 0. Now when lambda is equal to 3, 1 gives minus 1 0 minus 2 0 0. Put lambda is equal to 3 in this equation. Put lambda is equal to 3 in this first equation. So what we will get? Minus 1 0 minus 2 0 0 0 and 0 0 0. Okay, and that matrix is already in the row echelon form. Minus 1 0 minus 2 0 0 0 0 0 0. So we will get x1 minus 2 x3 is equal to 0. So x3 is equal to minus x1 by 2. So first column have leading entry, but the second and third column does not have leading entry. So we have to suppose x2 is equal to k and x3 is equal to t. That x2 is equal to k and x3 is equal to t. So x1 is equal to minus 2t. Right? Put these two equations, these two values in the previous equation. So we will get x1 is equal to minus 2t. So the eigenvector corresponding to lambda is equal to 3 is minus 2 0 1 and 0 1 0. Now taking all eigenvectors as columns, we form the matrix P. What is our first eigenvector? Here is the first eigenvector 1 0 0. Second eigenvector minus 2 0 1 and third eigenvector is 0 1 0. Put these three eigenvectors in this matrix as a column matrix. So 1 0 0 first column, second column is minus 2 0 1 and the third column is 0 1 0. Okay, that is our matrix P. Now you want to find P inverse AP, but you can directly write down the P inverse AP. The P inverse AP is exactly, now the first column, this first column in this P, first column as an eigenvector corresponding to lambda is equal to 2. So in P inverse AP, the first element is 2. In the second and third column are the eigenvector corresponding to lambda is equal to 3. So in the main diagonal, the first entry is 2, second entry is 3 and the third entry is 3. And all other entries are 0 in P inverse AP. If you want to check out P inverse AP, that is exactly the lambda 1, 0 0, 0 lambda 2 0 and 0 0 lambda 3. So that means 2 0 0, 0 3 0 and 0 0 3. If you want to find out, you have already P, you can find P inverse of matrix. That you should know that how to find inverse of matrix, right? And A is already given in the question, and P. So when we multiply P inverse AP, we will get 2 0 0, 0 3 0 and 0 0 3, right? Here is the question number 5b. Let R3 have the Euclidean inner product. Use the Gram-Schmidt process to transform the bases U1, U2, U3 into an orthonormal basis. So this Gram-Schmidt process is actually used to any basis convert into an orthonormal basis. So first of all, we have to find convert these three vectors into an orthogonal set and then orthonormal set. Okay. From orthogonal to orthonormal is quite easy, because we have to just divide it by the norm of each vector. That's it. But the main process is the convert from any basis vectors to orthogonal set, and that's why we have this formulas. let v1 is equal to u1, that is equal to 1 1 1. Then find the inner product with u2 with v1, that is minus 1 1 0 into 1 2 1, that is equal to minus 1 plus 1 plus 0, that is equal to 0. Okay, and now we want to find v2. Now what is the formula for v2? v2 is equal to u2 minus inner product u2 v1 upon norm v1 square into v1. We already find inner product u2 with v1, that is 0. So whenever we put this value minus 1 1 0, that is u2 minus 0 by 3 into 1 1 1, that is equal to minus 1 1 0. So v2 is minus 1 1 0. Now find because we have this formula, v3 is equal to u3 minus inner product u3 v1 upon norm v1 square into v1 minus inner product u3 v2 upon norm v2 square into v2. So we have to find inner product u3 v1, inner product u3 v2. So we want to find inner product u3 v1, that is equal to 1 2 1 into 1 1 1, that is equal to 1 plus 2 plus 1, that is equal to 4. Inner product u3 v2, that is equal to 1 2 1 minus 1 1 0, that is equal to minus 1 plus 2 plus 0, that is equal to 1. So 1 2 1 minus 4 by 3 into 1 1 1 minus 1 by 2 into minus 1 1 0. So 1 2 1 minus 4 by 3 4 by 3 4 by 3 plus 1 by 2 minus 1 by 2 0. So that is equal to 1 minus 4 by 3 plus 1 by 2, that is 1 by 6. 2 minus 4 by 3 minus 1 by 2, that is 1 by 6, and 1 minus 4 by 3 plus 0, that is minus 1 by 3. So now we have orthogonal set. v1 v2 v3 are orthogonal set, but we want to convert into a orthonormal set. Okay, so that's why we have to divide it by norm of each vector. Norm v1 is equal to root 3, norm v2 is equal to root 2, and whenever we find norm v3 is equal to 1 by root 6, right? I already explained that how we find norm v1, norm of any vector with the Euclidean inner product. So you know that norm v1, what is v1? v1 is 1 1 1. So norm v1 is under root 1 plus 1 plus 1, that is under root 3. What is v2? v2 is minus 1 1 0. So norm v2 is equal to under root 1 plus 1 plus 0, that is under root 2. And v3 is 1 by 6 minus 1 by 3. So norm v3 is equal to 1 under root 1 by 36 plus 1 by 36 plus 1 by 9. Whenever you solve it, you will get norm v3 is equal to 1 by root 6. Divided by norm of each vector v1 v2 v3. So the required orthonormal basis is given by v1 upon norm v1, comma v2 upon norm v2, comma v3 upon norm v3. So that is, you will get the first vector is 1 by root 3 1 by root 3 1 by root 3. The second vector is minus 1 by root 2 1 by root 2 0, and the third vector is 1 by root 6 1 by root 6 minus 2 by root 6. And if you want to check that these three vectors are orthonormal or not, you have to check inner product of any two vector should be 0 and the norm of any vector is equal to 1. Okay, so this question is complete now, and here we complete the solution of June-July 2011 of the subject of vector calculus and linear algebra. Thank you.